All right, hello guys. My name is Felipe Grael. I am from a prototype and support team for Catesi, and I have a long background on machine learning and building models for prediction and unsupervised models for clustering. And I've recently joined Catesi, and I'm going to talk about LLMs and machine learning models on-chain, out of the box, with existing libraries and existing tooling for the machine learning. Okay. May I use the clicker here? All right. So why using machine learning on-chain in the first place? What would be the advantages of doing the computation on-chain, right? So the first very big advantage is to have the fully verifiable computation. So you can, given the certain input, you can be sure that the output is going to be the given output because you can verify all the computation at all steps. And you can even build further on this and use explainability libraries and explainability techniques to actually open the black box of machine learning. So machine learning is very well regarded, but there are people who still have some kind of doubts of how is it actually going to work, because it's like a black box, no one can see inside what it's actually doing. And you can actually open the box and show what's being important and why the machine learning algorithm is given a prediction. And doing this on-chain is even better because you can guarantee each computation. The second thing is that you have a commitment to quality, and your application is going to be committed to delivering a good quality model because everything is going to be on-chain, even when the model fails. So you know that machine learning doesn't always get right, sometimes it gets wrong. So the failures is always also going to be on-chain. So you need to have a procedure to work around the failures and to fix any kind of decision made with bad prediction. And once you have all the data input on-chain, the output also recorded, and the information that if you made some mistake or not, you're also creating a new data set for training. And then you have more data for further improving your model and further improving the application itself, right? And this is a very good way to build trust from users. So the users are going to trust our application more because they can see transparently everything that's being done and everything that's going to take place. And we have a true decentralization. I mean, you can always host your model off-chain. You can always send to a centralized server and do the inference over there, and then come back with the results or come back with a hash and tell the user, okay, you can verify it on your own. But once you do the machine learning computation on-chain, verifiably, you actually have a true decentralization. You don't need this centralized piece, which comes with a host of problems. So you can get your DApps really more powerful, bringing real machine learning inference to your DApps. Okay. But there are some challenges to it. And the main challenge is how big of a computation you can actually do. Machine learning models come in very different sizes. If you take a very simple machine learning model, such as a regression model, maybe just a few multiplications and additions solve the problem. You could even implement it on Solidity. It's not a problem. But once you get to a certain scale, it's unfeasible to do it on Solidity. Only the gas prices for the computation is going to be too much. And sometimes it's even not even the gas price the problem. The models can get very, very large very quickly. So for example, the Llama, which is a large language model, even the smallest size, the small large language model, is still 7 billion parameters. It still takes 28 gigabytes of memory to compute, to make the computations feasible. You can even approximate to integer, and you still have 3.5 gigabytes. So even with approximations, it's still very large for us to do with regular tools. And also, you see, machine learning has a very big community already. We already have very well-established tools and very well-established libraries, like TensorFlow, PyTorch, and scikit-learn. They are made on top of regular programming languages like Python, C++, even Fortran, which is a very old language, but just to know that the tools are very well validated by the academic community as well. That's why they use this kind of languages. And one thing that I thought is that, okay, even for smaller models, you could implement in Solidity, but should you actually? Because if you use existing tools, you're going to use existing very well validated by the community. And if you build your own, you could introduce errors where you could avoid it, right? So what if we could actually use existing machine learning tools, existing libraries, with all the security and advantages of the blockchain? So this is where we can use the Cartesi virtual machine, where you have an application-specific rollup. Each application has its own dedicated rollup, and your code runs inside a virtual machine, which has been stripped down of all entropy for it to be reproducible. And this virtual machine runs the RISC-V processor. RISC-V is an architecture, is an open source architecture. It's widely supported. It's even supported by the Linux kernel. So you can actually run Linux inside this virtual machine. And once you have a Linux running inside a virtual machine, you can use whatever language you want, whatever library you need to. So you can use existing machine learning tools, right? So an overview of the solution would go to be, you have a browser with the front end, for example. The browser would send inputs on chain, on an EVM compatible chain, including Gnosis, of course. And the input is going to be captured by the Cartesi rollup. The Cartesi rollup sends the input inside the virtual machine. It's going to make the computations, and then the state of the virtual machine is going to be sent back to the layer 1. And everything is going to be verifiable. If you need to dispute, there is a very extensive protocol for disputing in the Cartesi machine, and you can pinpoint exactly which instruction differs from one another. Okay? We have already made some very good examples with several libraries like OpenCV for computer vision, NumPy, SumPy, scikit-learn, which is a very classic and very well-established libraries for scientific computation in Python, and the SciPy with the scikit-learn, sorry, with very common machine learning algorithms. TensorFlow Lite is also working very well on the RISC-V processor, and it allows us to make inference on even deep learning models, some deep learning models. Okay? And also, if you have some bespoke code which was made in C++ or any other language, you can also just compile for RISC-V and then run inside the virtual machine. Right? So several use cases have already been made. I'm going to show 2 use cases, and then I'm going to show a video of how we do one specific example and how it looks like. Okay? So this one is the Alpaca LLM running inside the virtual machine, the Cartesi rollup. For this example, we actually took the specific code made in C++ for the inference on the Alpaca, and then run it inside the virtual machine. This is actually a project from ETH Global Lisbon. It was also a finalist in ETH Global Lisbon. The advantage is that you're going to have the full traceability and full verifiability of the inputs and outputs. So whenever someone gives a prompt, the the resulting text is going to be verifiable on chain as well. So there is no denial that the response was what was given as claimed to be. So it adds another layer of accountability to the application running the solution of LLM. Another very interesting example is, for example, for identifying identity through biometrics, through fingerprint identification. And the group that did this also was a very good example because not only they identified the fingerprint based on the image, but it also could classify if the image was of an actual fingerprint of an actual person or was something scanned or some kind of scam that the user is trying to pass by the system, right? So this uses OpenCV for computer vision and C++ code that they develop using their own computer, their own expertise, their own original tooling, and then can simply put inside the Cartesi VM for application on chain, right? And yeah, then we have a really small demo. So is it playing on? Okay, how do I pause it? Can I just pause it then? Yeah. Okay, so no problem. So here in this demo, I'm going to show a little bit of the source code for the application. And also, okay, can you just pause in the beginning, please? Let me. So you see the file model.pkl. This file is the model that was previously trained and saved as a Pico file. And then the code to the right is going to load the model and make the inference, right? So for training the model, you can use all the rigor of training machine learning. Thank you so much. And then in the source code here on the side, you can see where we open the file and load the machine, the model to memory, and then the inference part. And here, down here, you just have the code for the advanced state, which is the code that actually, can you pause there, please? Okay. This is the code that actually interprets the input sent on chain, and it's going to do the prediction and then send the value back on chain. Okay. So the first thing it's going to send is a log to the output, and then it's going to send a notice that's the thing verifiable on chain, right? So once we put the application to run on top, we can send an input. The video, the bottom part of the video is showing? Or? Okay, so the bottom part of the video, I'm just typing here a phrase to send on chain. The phrase is, this is a great demo. And then you can see the logs up there saying this is a great demo and the prediction is positive for sentiment analysis, okay? So this is a sentiment analysis demo, okay? And then I'm going to type another one. You see here the verification on the graphical of Cartesian machine, okay? And then I'm going to type another one. It's like last week I saw a very terrible movie, and we're going to see what the model predicts as a sentiment. So the moment the transaction is sent with this payload, you can see over there, the movie I saw last week was terrible, is negative. So you see the prediction on chip. Okay. So yeah, the biggest part is that the programming for this is very simple. We're just using a very regular scikit-learn way of doing things. Anyone studying machine learning should probably one of the first steps should be to create a model with scikit-learn, which is a very simple library to use. So we didn't have to make any kind of modification to this, to the flow of the machine learning programming to use it in an application, a real distributed application. And so this is just a demonstration to show how easy it is to integrate this stuff. Okay? And we are going to be on ETH Global this weekend. If you guys are interested, feel free to reach out. I'll be around. Okay? Thank you.
Do we have any questions or any comments about what Philippe was just talking about? No? Well, we have one. Okay.
Do you have some? Oh, sorry. Do you have some rough numbers? Like, doesn't really have to be benchmarks, but like number of constraints versus network size, like, or what type of things can you prove?
Okay, this is a great question, actually. We did try some pretty large models already. It's not going to be a little bit slower than doing it on CPU. So yeah, so it's going to be like 10 times to 15 times lower than doing CPU, but it still have the advantage of having a very predictable computation. Okay. There is, of course, a limit to how big it can go. So maybe not every model, not the biggest model that you could find, for example, in huggingface.org. But I don't really have a number, but I have already tried successfully some models which are like 200 megabytes or something like that.